Welcome to the deep dive. This is the essential briefing for you, the professionals, the enthusiasts, everyone tracking innovation right at the edge.
Yeah, thanks for having me.
Today, we're diving into something pretty fundamental, how AI is radically changing materials science.
It really is a huge shift.
And this is critical stuff, understanding the groundwork being laid before AGI really shifts the landscape.
Absolutely. We're not just talking about tweaking things in the lab. This is a root and branch overhaul of how we discover the building blocks of technology.
Things like next-gen batteries, catalysts, semiconductor.
Exactly, all the foundational stuff.
And the core problem, the reason this is such a big deal, it really comes down to time, doesn't it?
It does. Traditionally, finding a new material and getting it into a real product, you're looking at an average of 20 years.
20 years. That's a huge delay. It holds back everything from, say, clean energy tech to faster computing.
A massive anchor, yeah. But what our sources are showing, and it's really clear, is that AI is just collapsing that timeline dramatically.
So instead of decades,
we're talking weeks, maybe months. It's because AI is automating and, crucially, integrating the core steps of discovery.
Right. So that's our mission today. We want to unpack this AI discovery engine. We'll look at, first, the generative models, the creative part.
The idea generators.
Then second, the property prediction models. That's the high-speed filter, right?
Yep. Sorting the good from the bad quickly.
And finally, the autonomous labs that actually, make and test the stuff, closing the loop.
The physical validation. That's a whole system.
Okay, let's jump in. Component one, the creative chemists, the generative models.
So generative AI in chemistry. It's not just about modifying materials we already know. That's old news.
Right.
This is about AI acting as a genuine creative engine. It proposes completely new structures, things human intuition might just miss. It's exploring vast chemical spaces from first principles.
And the tech that's really shining here, maybe surprisingly, is diffusion models. The same kind of thing behind AI art generators.
Exactly the same principle, yeah. It's proven remarkably effective. A diffusion model learns to sort of denoise a random starting point.
Okay.
It keeps refining it until you get a stable, coherent form. And Microsoft Research used this for MatterGen.
MatterGen, okay.
It's a diffusion model specifically trained to generate stable, diverse, inorganic materials, across the periodic table.
And this is where you see the real impact, right? The number.
The numbers are stark. MatterGen's generated structures. They're more than twice as likely to be genuinely new and stable compared to older computational methods, like brute force searching.
Twice as likely. That's significant.
But the stability metric is maybe even more telling. MatterGen's creations were found to be over 10 times closer to the local energy minimum.
Wow. Okay, break that down. What does closer to the local energy minimum mean for us?
It means the structure the AI proposes is much more physically plausible. It's inherently more stable. It needs way less computational tweaking afterwards to confirm it could actually exist.
So it's inventing stuff that's chemically sound right from the start.
Pretty much, yeah. Robust stuff.
Now, what's also fascinating is how versatile these AI tools are. We usually think of large language models, LLMs, for text, right? But you mentioned Crystal-LLM. How does a language model write chemistry?
It's clever. It treats the standard file format for crystal structures. It's called a crystallographic information file, or CIF.
CIF file, okay.
It treats that CIF file like a language. It has its own grammar, its own rules. A CIS is basically just a text file describing everything precisely. Atoms, positions in 3D space, orientation.
So the LLM learns the grammar of crystallography.
Exactly. It learns the structure, the syntax.
Yeah.
And then it can generate a physically plausible crystal structure, coordinates and all, just by essentially writing a valid CIF text file.
That's a brilliant crossover, applying text generation to chemical generation.
And it gets even better when you bring physics back into the mix explicitly.
How so?
While models like PGCGM, that's physics-guided crystal generative model, they actually integrate fundamental physical laws and constraints into the deep learning process itself.
Ah, so it's not just learning patterns, it's learning patterns within the rules of physics.
Precisely. And doing that, it increased the validity, the physical plausibility of the generated structures by over 700% compared to earlier AI models that didn't have that physics guidance.
700%.
Yeah. So blending deep learning's power with known physics, huge boost in quality and speed.
Okay, so component one, the generative part, is spitting out potentially millions of candidate materials, maybe one every second.
The scale can be immense.
Right. And we obviously can't run a full detailed simulation or, a lab experiment on every single one. That would take forever.
Absolutely not. That's the bottleneck we needed to solve.
So we need a filter. How does AI rapidly sift through these proposals?
Exactly. That's the job of property prediction models. They act as this crucial high-throughput filter. And to understand the filter, you really need to understand the main architecture being used. Graph neural networks, GNNs.
GNNs seem to be everywhere in AI lately. Why are they such a natural fit for materials?
Because crystals are graphs, fundamentally.
Yeah.
Think about it. The atoms are your nodes,
Okay.
and the chemical bonds between them are the edges connecting the nodes.
Right. Makes sense.
And GNNs are just really good at analyzing relationships and local environments within networks like that. So sophisticated models like, say, LIGN,
AI.
it captures specific bond information using something called line graphs. Or another one, DensGN,
Yeah.
uses dense connections to help information flow better. These models can look at the structure graph and rapidly predict key properties.
Like stability,
Yeah.
conductivity, hardness, that
Yeah,
kind of thing.
Exactly. Based purely on the structure,
Right.
no full simulation needed at this stage, just a fast prediction.
Okay, let's dive into some jargon that comes up a lot here. Machine-Learning Interatomic Potentials, MLIPs. You mentioned MACE, MP0, and CHGNet. People talk about running simulations at near-DFT accuracy. Can you quickly unpack DFT and why MLIPs are such a big deal?
Sure. DFT stands for density functional theory. It's basically the gold standard for computationally simulating materials at the atomic level. Super accurate. But it's incredibly slow and computationally expensive. A single DFT calculation might take days, even weeks, on a supercomputer.
Okay, definitely a bottleneck.
It was the bottleneck for large-scale screening. Now, MLIPs are the breakthrough. They're often foundation models,
Meaning?
meaning they're trained on vast data sets, millions of those expensive, high-accuracy DFT calculations. They essentially learn the complex physics from that data.
Okay, got it.
And once trained, these MLIPs can predict the energy and forces, basically run a simulation with almost the same accuracy as DFT.
That near-DFT accuracy.
Exactly. But instead of days or weeks, they do it in milliseconds or seconds.
Whoa. That's, the analogy you used before flying versus teleporting.
That's pretty much it. It changes the entire economics of computational screening. Speed and accuracy.
And this leads towards these bigger multimodal systems, right? Like
Hmm.
IBM's FM4M. What makes it a foundation model for materials?
It's about versatility. It's modular. Instead of just training on, say, the 3D atom positions, FM4M can understand multiple ways of representing a chemical, like smile strings. That's like a text-based fingerprint for a molecule. Or graph representations. Or the 3D positions. It integrates all these views for a more holistic understanding.
More complete picture.
Right.
Right.
And connecting this back to how people might actually use it, models like ChatGPT are showing the way for text condition generation.
Meaning you can just type what you want.
Pretty much. You describe the function, I need a stable catalyst for X reaction at Y temperature. And the model starts generating candidate structures designed specifically for that job.
That really closes the gap between human intent and the AI search, doesn't it?
It streamlines the whole process immensely. And all this enables a really fundamental shift in thinking. For decades, science was mostly forward prediction.
Meaning propose a material, then predict its properties.
Exactly. The new way, enabled by AI, is inverse design.
Okay, so flip it around.
Right. You define the property you want. First, high stability, specific conductivity, the right band gap, and then you task the AI. Find me the structure that delivers this property.
That sounds much more targeted. But it must require complex workflows, right?
It does. You need integrated systems.
Mhm.
We're seeing AI agents that execute this. For example, Invitas Flow.
What did that do?
It combined deep learning and diffusion models in this inverse design loop. And it discovered 74 potentially new, thermodynamically stable, high-temperature superconductors.
74. Just like that.
Well, computationally discovered. Still needs verification, but yeah. Or look at Designer, they call it a Chemist AI agent.
An AI chemist.
Powered by LLMs, yeah. It actually uses insights from scientific literature, just like a human researcher would, to guide its iterative search for materials with desired properties.
Okay, but this creates a new problem, doesn't it? If the AI can screen candidates incredibly fast.
It completely outpaces our ability to actually make and test them in the lab using traditional methods.
Right. If the AI finds a million good ideas in a week, but a human chemist can only synthesize and test, say, 5 candidates in a month.
The whole pipeline grinds to a halt right there. The computational speed is useless without matching experimental speed.
Which brings us to the crucial third component.
Exactly, the autonomous laboratory. the self-driving lab. This is the essential physical infrastructure needed to close that loop.
So robots and AI working together in the lab?
Precisely, integrating robotics, specialized synthesis equipment, and AI to actually run the experiments, validate the predictions, characterize the results, all without direct human intervention 24/7.
And the prime example here is the A lab at UC Berkeley. Those results were pretty stunning.
They really were a landmark. The A-Lab system ran continuously for 17 days straight.
Wow.
And in that time, it attempted to synthesize 58 different novel compounds predicted by AI. It successfully made 41 of them.
41 new materials synthesized autonomously. That's a success rate of
71%, which is remarkable in itself for novel material synthesis. But the key wasn't just the success rate, it was the autonomy.
It wasn't just a robot arm mixing things.
No, it was an entire intelligent loop.
Yeah.
The AI predicts a target. Another AI model, maybe an LLM trained on chemical literature, generates a plausible synthesis recipe. The robotic system executes that recipe. Then, and this is critical automated characterization tools, like X-ray diffraction, analyze what was actually made.
And feed that data back?
Immediately. The results, success or failure, what was actually produced, get fed straight back as new data points to refine the AI models for the next experiment in the sequence.
So it's a continuous self-correcting cycle, learning and improving on the fly.
That's the dream, closing the loop completely.
So pulling this all together, what kind of scale and real-world impact are we seeing? This isn't just theoretical anymore.
Oh, absolutely not. The scale is probably the biggest story right now. Look at Google's GNNs project.
GNNs, right. What were the numbers there?
In one single computational campaign, GNNs discovered 2.2 million new crystal structures.
2.2 million.
Yeah. And within that, crucially, were about 380,000 predicted to be stable materials, potentially useful for future tech.
380,000 stable materials. Just put that in context. How does that compare to what we knew before?
It vastly expanded the known map of stable materials. It represents something like, potentially centuries of traditional experimental discovery done in a relatively short computational project.
That's staggering. And for the listener, why does this matter? Where are we seeing concrete applications emerge?
Batteries are a big one. AI screening has already identified 5 new types of porous oxide materials.
Porous oxides. What makes them special?
Their structure is like a sponge at the atomic level. It makes them potentially ideal for high-capacity batteries using magnesium or zinc ions, which are bulkier than lithium, but could offer higher energy density or safety.
Okay, so better batteries. What else?
Advanced polymers. There was a study using a GPT-style generative model to design polymer electrolytes for solid-state batteries.
Solid state, the next big hope for batteries.
Exactly. They generated candidates, tested 46 of them experimentally. 17 performed better than the known standard materials.
17 out of 46, that's a pretty good hit rate.
It is. And some of those actually double the ionic conductivity compared to the previous best. That's a huge jump for solid-state performance.
Doubled conductivity. Wow. Any other examples?
Catalysts are another key area.
Yeah.
There's a model called Catalyst GFlowNet. It was tasked with finding good catalysts for producing hydrogen, a critical process for clean energy.
Okay, what did it find?
Well, the really compelling part is that in its search through chemical possibilities, it independently rediscovered platinum,
Platinum, which is?
which is the best, most well-known catalyst for that specific reaction, discovered through decades of human trial and error.
So the AI, starting from scratch, basically, found the optimal solution that humans already knew.
Yes, it validates the AI's search capability. It proves it can systematically explore the chemical space and identify top performers, potentially even better ones we haven't found yet.
Okay, so the potential is enormous, the acceleration is real, but there have to be challenges, right? It can't be completely solved yet.
No, definitely not. There are still significant hurdles before this becomes, standard practice everywhere.
What's the biggest one?
Data is still a core issue. Getting high-quality, consistent experimental data to train these models is hard. It's expensive, it takes time, and results can vary between labs.
Garbage in, garbage out, basically.
To some extent, yes. If the training data is messy or sparse, the AI's predictions will suffer, especially for more complex properties.
What else?
There's the challenge of out-of-distribution performance.
Oh, out of distribution.
It means if you train a model on one family of materials and then ask it to predict something about a completely different, really novel type of material, it's never seen anything like before.
Its accuracy drops off.
Often, yeah. The models can struggle when they go too far outside their training experience. Making truly novel discoveries is still hard.
And then there's the interpretability issue, the black box problem.
That's a big one for adoption. Deep learning models are powerful, but it's often hard to understand why they made a specific prediction.
And scientists want to know why.
Exactly. Material scientists rely on physical intuition and understanding mechanisms. They're hesitant to trust a prediction if the AI can't explain the underlying physical reason for it. They don't just want the answer, they want the rationale.
Fair enough. Anything else?
The final big one is the synthesizability gap.
Ah, right. Just because the computer says it's stable.
Doesn't mean you can actually make it in a real lab with real-world chemicals, temperatures, pressures. Predicting whether a computationally designed material is practically synthesizable is still a major challenge. Bridging that gap between theory and practice is key. #tag outro.
So let's sum up. This isn't just incremental improvement. AI-accelerated materials discovery is fundamentally changing the process. It's moving science from being, well, often intuition-led,
Trial and error.
to being a much more data-driven, systematic engine for innovation. This ability to combine AI creativity, high-speed filtering, and autonomous validation.
It's becoming table stakes. It's rapidly turning into essential infrastructure if you want to stay competitive technologically on a global scale.
Absolutely. And looking ahead, what's on the horizon?
Even more acceleration, I think. We'll see tighter integration with other advanced tools. Imagine combining these AI systems with, say, quantum computing for even more accurate simulations of complex molecules.
Wow. Okay.
And the ultimate goal is realizing those fully closed-loop discovery systems, labs that run continuously, designing, making, testing, and learning 247 adapting experiments with minimal human oversight.
A true lights-out discovery factory.
That's the vision. This revolution in how we find and create new materials, it really feels like it's only just getting started.
Well, we hope this deep dive into AI's creative chemistry has given you some clarity and useful insights for tracking this incredibly important frontier.
Hope so too.
If you do want more AI content, things like tutorials, deeper analysis of what's emerging, definitely check out the YouTube channel. It's called Ian Ochieng AI.
That's I-A-N, then O-C-H-I-E-N-G.
Right, pronounced Ochieng, Ian Ochieng AI on YouTube.
Worth checking out.
Thanks so much for joining us on the deep dive. We'll be back soon with another essential briefing from the edge of innovation.